Hi, in this video, I'm going to be introducing conceptual topics around inferential thinking. Thinking inferentially implies that we are using a certain amount of data, as well as using a certain amount of hypothesizing or ideation, theories, developing hypotheses, developing ideas that don't necessarily have to be based on observation, but rather on it could be based on creativity or past experience or retesting of previously asserted claims and building models of thinking around the two. For example, in hypothesis testing, what we do first is we create a theory about a mean or a proportion, or about some sort of parameter of interest. A parameter of interest is a metric. It's a metric of something that we find relevant or interesting about some process or some phenomenon or some event that we are trying to understand better. And this usually goes by the definition of what we call a null hypothesis. And what we ultimately want to be able to do is to make one of two possible determinations about these hypotheses. We either want to be able to reject this hypothesis so that we can outright say, based on our thinking, this is just not a good idea, or this is just not a solid way of thinking about the world, and we should come up with an alternative way of thinking about the world. Or where we fail to reject, and we can therefore maintain that this idea is possibly our best understanding up to this moment about that. And whether we reject the null hypothesis or we fail to reject the null hypothesis, one of the most relevant things to remember about this way of thinking, inferential thinking, is that we're not making an absolute determination about this parameter of interest. So we're not really identifying truth or falsehood in an absolute sense, but rather we're relatively discerning which way we lean on a perspective about this idea. Obviously, we would love to know the truth. So we would love to establish if we have a true null hypothesis or if we actually have a false null hypothesis. So that's but those are ideals. Those are not attainable through inferential thinking or through the scientific method. It could very well be that we observe, after taking into consideration new data, a reversal of these particular assessments. So neither hypothesis testing nor confidence interval nor scientific thinking in general establishes truths in an absolute sense. They only establish a truth in a relative framework, or another way of saying it as well is establishes truths with some reasonable level of doubt based on the fact that we're not omniscient and ever-present and have access to the universe of data and all of its possibilities. So what can occur here are situations where we reject a theory that is false, in which case we assess things correctly. So rejecting a false theory is what we do with what we call confidence. Building confidence intervals, for example. And we can also correctly fail to reject true null hypotheses. And that's something that we call power. So these probabilities of confidence and power are hopefully high probabilities that enable us to therefore reject falsehoods and not reject truths in high regard or high probability mechanisms. When we reject a truth, that's when we commit something that we refer to as a type 1 error. And a type 1 error comes with a probability that we essentially choose, that is of our choosing. And we call that probability by the Greek letter alpha. That probability is a complement to the probability of confidence. So given that a rejection is evident by the data that we employ in making assessments, under uncertainty, alpha and 1 minus alpha correspond to the probability of a type 1 error, the probability of a reasonable doubt, which is how we set this. And we also now have another pair of probabilities denoted by the secondary Greek letter beta. And we refer to that probability as a type 2 error probability. And the power of a test is the complement of this beta. So two potential sources of error in our inferential thinking, type 1 and type 2 errors, rejecting truths or accepting falsehoods, to put it in a less precise but easier to remember rhythmic context or rhyming context, and two correct decisions when we reject falsehoods or fail to reject truths. The only thing that can make our models reduce both alpha and beta is larger data samples that are valid. What are larger data samples that are valid? Samples that are random, independently observed values, that are not too small, meaning that the sample size happens to be, I should say, not too large, that the sample size is no more than 10% of the population size. Not too small, and the nature of not too small varies from context to context. It could also be that the data sets should be devoid of outliers or exceptions. Too many exceptions require more and more data and more study and more repetition of these activities to create greater rigor and to create greater resilience in our thinking and in our results. So the more outliers we see, the worse our theories fare in inferential thinking. because more exceptions to rules make rules less likely to be true, and theories tend to be uh, rules about or patterns in system designs or in nature of things under study. So you don't want the data set to be too small. You want it devoid of outliers. You want the data to be relatively symmetric. The more skewed the data, the harder it is to treat it in inferential thinking methods and mechanisms, although it does not by any means make it impossible to make assessments about skewed distributions. And in fact, this is essentially a map then of what you study in chapter 13 of your textbook, a map of the subject matter of hypothesis testing and confidence interval estimation. I hope that this brief introduction to chapter 13 helps you complete both the lab work and the project that you have in this chapter. And take care.